Okay, so today I'm going to talk about the Dirac belt trick and related notion called Quaternions. And before I discuss the belt trick, I'm going to discuss a kind of simpler phenomenon. We're going to actually illustrate this so-called belt trick in two ways. One with an actual belt. This is not so suspenseful. And then we'll do the version that involves a bottle of liquid, in which I will take the cap off. That adds a little bit more pizzazz to it. And then, of course, the main focus is to try to explain where is the math content in this, right? And then how does it relate to these things called Quaternions? So the first thing I want to convey in a kind of simpler way is the following idea, that if you take an object with a sense of orientation and you move it through space in certain ways, it can come back to where it was, but the orientation is somehow twisted around. And so there's a very nice idea kind of illustrated by this picture on a sphere. So imagine you took a vector pointing straight up here, and you just slide it perpendicular to the surface of the sphere along these three paths. And so what would happen, so imagine that this point is sitting on the sphere, and then my hand is giving me a sense of my orientation in space. And as I go down the sphere, right, you go down like this when you get down to here, pointing out. And then when you move along this side, it's like this, and then you come back up. So now I'm back where I was, except I'm twisted, right? And then, of course, I can do it again, right? And notice now my hand is facing back. Now, of course, you're all wondering what's going to happen, right? So the next one I can kind of do. All right, but then, of course, the physiological obstructions get in the way, and I can't do it any further, okay? But I'm just pointing out that there's this phenomenon that if you're keeping track of the orientation based at a point, as you move through space, you can come back to where you were, and the orientation can be twisted around. Okay? Now, this gives rise to some surprising phenomena encoded in this thing called the Dirac belt trick. So we're going to do a demonstration of this with an actual belt, and then we'll do the more exciting version called the mug trick, or sometimes called the plate trick, but I prefer the mug version because spilling liquid is a little bit more suspenseful. Okay, so it didn't come on here. All right, so this is a belt. So he's going to hold the belt. Now, what I want you, so this is, let's rotate it around so it's not like this. Okay, so it's straight up like this, all right? Now I'm going to walk around him twice in the same direction, all right? Once going above his head, and the next time going below. Okay, so the first time I'm going to walk around, and then I come back, and you'll notice that this belt is quite twisted, right? Now I'm going to walk the second time, same orientation, but go below, and now the belt became untwisted. Let's do that one more time. Okay, so we go above, and then it's twisted, and then I again same orientation spinning around, and then it untwists. Okay, so that's called the belt trick, and of course one thing you may be thinking is, what just happened there? Okay, how did you make the untwisting go away? Thank you very much. Okay, so now we're going to do a more suspenseful version. So we have this mug from some company whose label is hidden for the purpose of not making this a product endorsement. Okay, so now I have this bottle of liquid in which I drank a little bit just because, so the idea is I'm going to move this around in a certain way, and in principle I should keep my hand absolutely parallel to the ground, so this is always pointing exactly up. But since, of course, there's going to be a slight wobble, which is why I drank a little bit of the liquid, but it'll be clear that in principle I could do what I'm about to do, keeping this pointed straight up all the time. And so here we go. Okay, so we're going to rotate around. Okay, and now we're going to... What? Okay, so let's do that again. It didn't spill. That's good. So notice the first time I go below my upper arm, right, keeping it straight up all the time. So the mug did a 360-degree turn in space, always pointed up, okay? And now we're going to go above, all right? And again, notice it's spinning around again. Whoa, okay? So what just happened there? All right, so the thing I want to point out is this is kind of analogous to the belt. In the case of the belt trick, the first time I went above his head, the second time I went above his hand, the second time I went below his hand. Here, my lower arm first went above my upper arm, and then it went, let's do it again, that was so exciting, okay? So let's do this one more time. Hopefully I don't spill it this time, all right? And then we come around, very good. Okay, so 2 questions are, what just happened there? And where is the math? Right? What is the math content of this? And so this is what I would like to explain. So to do that, I want to talk a little bit about how we keep track of rotations in space. Okay? Now, the thing I want to stress is, when I was doing this maneuver with my hand, it's true that the various points of my arm were moving around in space, but what's important is I'm just pointing out something about the orientation of my hand. So the purpose of the mug was just to emphasize the whole time my hand was staying parallel to the ground, but it was spinning around. Okay, and then again it span around the second time, but of course if I didn't have the mug there, you wouldn't believe I was keeping my hand perfectly flat, but the idea of the mug was to drive that point home. Okay, so in a sense, if you had a little orientation frame based at my hand, and I'll draw a picture, it was really spinning around the vertical axis 360 degrees twice, and somehow when it all came back, my arm, didn't break. Okay, so the idea of a spatial orientation is the following. So we're going to draw a picture of, so this is a vector I'll call I, and then let's say we'll do this way, we'll have J, which is perpendicular to I, and then let's say we'll have K, which is pointing up. Okay, and this is a so-called right-handed coordinate system. Fingers in the direction of I, J coming out of my palm, K is up. So let's say if you start here, and now you spin it around in space, keeping this point fixed, maybe the next time around the I will be this way, I'll call that I prime, and maybe the J will be pointing, I don't know, let's say that way, call that J prime, okay, I, J, and then K will be out of the board, and so then you would have your K prime that way. So if we have some motion of space that carries this frame of reference to that frame of reference, okay? And we want to encode this information, and one of the things we learn in linear algebra is the way that this is some kind of linear operation, it's a rotation matrix, and so this is encoded. So if I make the 3x3 matrix, whose first column is I prime, written in this reference frame, second column is J prime, written in this reference frame, and third column is K prime, written in this reference frame, then this matrix satisfies 2 conditions. R transpose is the identity. So this is some 3x3 matrix of numbers. And the fact that it's a rotation matrix encodes 2 things. Those columns are mutually perpendicular unit vectors. That's exactly this condition on the matrix. That's the first condition. And then the second condition, well, if this holds and we take the determinant of both sides, we see the determinant of R squared is 1, so the determinant of such a matrix is plus or minus 1. And when it's 1, it's orientation preserving, and when it's minus 1, it's orientation reversing. And so we also impose this further condition that the determinant is 1. Okay? So these are 2 conditions on a 3x3 matrix that encode the fact that it is expressing an orientation-preserving rigid motion of space. Okay? Now, you could look at this as some horrific system of 9 quadratic conditions on the entries of this matrix. Okay? It's pretty horrifying. And this is some cubic condition on the 9 entries. This is, of course, not necessarily a productive way to think about the meaning of this, but this is an algebraic encoding of the idea of a rigid motion of space. However, it's hard to work with this, but let's illustrate this with one example, which is, let's see what was happening. Let's pretend that's my arm. Maybe I have 3 fingers. And then I have the bottle in my hand. So let's imagine here's the top of the bottle. Okay? And the point is, you have, as my hand was moving in space, what was actually happening to the bottle? Let's ignore the spatial translation. Let's just pay attention to the orientation of the bottle as it was moving around. And what was going on there was that there was a vector going up, take the north direction, up, and what was happening is it was rotating around, right? And this happened twice, right? The first half of the trick, and then the second half of the trick. So we could introduce a rotation matrix, maybe we'll call it R of t, a 3 by 3 matrix, R 2 pi t, 0, 0, 1, where R theta is a 2 by 2 rotation matrix by an angle theta counterclockwise. So if we consider this for t going from 0 to 1, that's the first half of the trick. You keep the third basis vector fixed, and this is a rotation around that axis for one of the two orientations. Okay? And if you allow t to go over twice as long, or better yet, just put a 4 pi here, okay? Then from 1/2 to 1 is the first step of the trick, and from 0 to 1/2, and then from 1/2 to 1 is the second step of the trick. Okay? So this is a collection of rotation matrices, admittedly not so complicated looking, that encode what's happening at the far end of my arm during this entire trick. Okay? The mathematical content of what's going on in here is going to emerge when we look at what was happening along the other points of my arm throughout the trick. But I just want to stress that this is a kind of a family of rotation matrices that's encoding spinning around twice in space around the vertical axis. Okay, so this is what I wrote before in terms of matrices was what you might call a kind of matrix viewpoint on rotations. Now I want to give something much more geometric, which is called the axis angle viewpoint on rotations, which is due to Euler. So let me call this the axis angle viewpoint. So Euler proved the following fact, that if I give you any rotation matrix R, and again, whenever I say rotation, I mean orientation preserving rigid motion of space, fixing the origin, then this is always rotation around some line through 0 by some angle. So the picture would be, let's say here's the origin, so you have some line, and then now you're going to rotate either this way or that way, okay? And just to get this consistent, so if I choose the unit vector in this direction, then maybe I'll call that u, and then I may have an angle, some angle, let's say alpha, around, and this is kind of counterclockwise relative to this point of view. If I was going to consider rotation going the opposite way, then I may keep track of the line using the opposite unit vector. There are two unit vectors on this line. Okay? So in this way, I encode every rotation in terms of a unit vector and some angle, where this is understood to encode a counterclockwise orientation when I consider the plane perpendicular to that line, and I orient space where this is the third basis vector. And then I look at what's happening in this plane. I want it to be counterclockwise. If I was doing the other rotation in the other direction, then I would put the unit vector on the other side, and then it would look counterclockwise from the other side of the plane. Okay? So in this way, I can encode orientations in terms of a non-zero vector and some angle. Okay, well that's really nice. So this is going to give us a way to visualize what you might call the space of all orientations. Now I should say, by the way, this theorem of Euler ultimately comes from a very concrete algebraic fact, which is the characteristic polynomial of a 3 by 3 matrix is a cubic polynomial. Cubic polynomials over the reals always have a root. So any matrix, any rotation matrix must have a real eigenvalue, but because it's length preserving, there's no stretching, the eigenvalue is either 1 or minus 1. And then you do a little bit of algebra. If minus 1 is an eigenvalue, the other two eigenvalues cannot be a conjugate pair, because otherwise the product of all three would be -1, but the determinant is +1. So there have to be other real eigenvalues, and they can't all be -1, or else their triple product would be -1, blah, blah, blah. Okay? So the upshot is there has to be an eigenvalue of 1. That means there's a fixed line. And then by the rigid geometry, it must be rotation relative to a plane perpendicular to that line. and then you orient yourself so that it looks counterclockwise. Okay, so that's where that comes from, this axis angle viewpoint. And this gives us a visualization, what I'm going to call SO3. So this is the collection of rotation matrices, R, as follows. So I would like to consider the totality of all rotation matrices, this kind of these 3 by 3 matrices satisfying these horrific algebraic conditions. I'm going to now use this axis angle perspective to give us a way to visualize the space of all rotations. I'm not trying to visualize R3. I'm talking about visualizing the collection of all rotations. So how do we do it? So let's consider a solid ball, 3-dimensional solid ball of radius pi. And for any point in it, let's say here's the origin, and for any point in here, maybe I'll call this V, which is not 0, what I'm going to do is I'm going to associate to V the rotation around the line through V by the angle length of V. And remember, we set up our convention so we always do the counterclockwise, so there's no ambiguity about which way you go. So in other words, if you're very close to the origin, your vector is very small, that means you've barely done anything. 0 will correspond to the identity, and as I move out towards the edge of this solid ball, I'm encoding rotations that go by more and more of an angle. Now what happens if you rotate by pi? Well, that's the same thing as rotating by minus pi in terms of the end effect. So what you do is you take the solid ball and then you identify what we call antipodal identification on the boundary. So as you move towards the edge, it's like you're rotating more and more. But if you get to the end, then you can pop out from the other side and then keep going. So in other words, for example, if you have a path that goes like this and then comes back the other side, what you're doing is you're rotating, right, around some axis by more and more and more. And now once you go past 180 degrees, right, let's say you go to 270 degrees, well, that's the same thing as minus 90 degrees. Okay? So if you go out to the end, you come back the other side. So the totality of all rotations of space can be viewed as a solid ball whose boundary has had opposite points identified with each other. Okay? Now I claim that this space has a very interesting geometry or topology, but in order to motivate how we're going to analyze it and to connect it back to this crazy stuff I was doing with my arm, I want to actually look at a 2-dimensional example, and this is related to the famous video game that perhaps none of you have heard of called Asteroids. Have you guys heard of Asteroids?
Yeah.
Good. Excellent. So when I was 9 years old, Asteroids came out, and it was, of course, the biggest hit that Atari ever made. And what I didn't appreciate when I was playing Asteroids was that I was actually playing a video game on the surface of a one-hole donut. Okay? So I want to illustrate this, and then we'll come back to the ball. So what happens in Asteroids? So the game of Asteroids takes place on a TV screen or some monitor, and you're some spaceship moving around, and then there are these various asteroids that come from different directions, and then you want to avoid them or shoot them, and they break up into pieces. But the gist of the game is that if you move off screen here, then you come out over there. Okay, so if you ever reach the end, you come back. So if you go off this way, then you come out that way. Okay, so you're constantly moving around in this funny world. Now, what's going on here? Let's draw it a little more cleanly. So what you're doing is this side and this side. This point is identified with this point. This point is identified with this point. And so we just draw something like this, where we understand that this edge is identified with this edge with corresponding points the same height identified to each other. Okay? It's like you take a flat piece of paper and you wrap it around to make a cylinder. Okay? On the other hand, along the top, something similar happens. This point is identified to this point is identified to this point. We draw a different set of arrows just to not confuse the two. And you take the piece of paper and you wrap it around that way. Now, if you do this, you take your flat piece of paper, and first you wrap it around into a cylinder, and let's pretend the paper was flexible, and then what you do is you identify the two ends together. That's like doing the other pair of edges. And so then what you wind up getting is the surface of a donut. Okay? So this game of, the thing I want to stress is the game of asteroids, you're playing on what seems like a flat space, but actually the topology of your space has a hole in it. You don't see the hole from this point of view, but from the outside you kind of can detect it. All right? Now here's the interesting thing. So in this game, let's think about taking your spaceship and just constantly moving up at constant speed. Okay? So first of all, I should say, by the way, that these two things correspond to, maybe you glued that way, and these two edges glue to that. So the two edges show up, and this point here corresponds, all the corners are identified with the same point. Okay, so this is the assembled gluing, and the thing I want to stress is if you now took a path in this space that went from here to here, then on the surface of the donut, you would be wrapping around, something like this. Okay? And if you keep going up, you keep going around and around and around. Okay? Great. So, and the same thing the other side. If you went around this way, then you go around the hole and you keep going around and around and around. Okay. So, in here, we see that a path that goes from top to bottom is a closed loop in this space. Right? On the donut, it's actually a loop. And if you look at it from that point of view, you see that no matter how you try to move it around in the space without cutting it, you can't make it shrink to a point. It's just stuck there. You may stretch it around, but you can't somehow shrink it and shrink it and shrink it arbitrarily. It's kind of stuck. Okay? What happens if you do this twice? If you go up twice in a row, then you've wrapped around twice and you're even more stuck. Okay? All right. Now here's the beautiful thing. I claim in the world of the rotation space, if you take a path that goes from end to end in a certain way, you still can't undo it, just like here, but if you do it twice, it can be shrunken down to a point. Okay, so this is the part that we're going to now visualize. Now, how is this picture different from the case of the ball? In the ball, we identified opposite points. Here, the antipodal point relative to the center, like this would be this, right? This would correspond to that, right? So this boundary identification, the geometry of it is completely different from the case of the ball that described SO3, right? In the ball case, we're identifying pairs of opposite points. Here, relative to the boundary, that would be like this goes to this goes to this, that goes to that, which is not what this is. Okay? So I can't describe, of course this is a surface, we can readily visualize it, the case of the ball is quite different, but I just want to stress the fact that the behavior of loops when you double them being non-contractible in this case is fundamentally different from now what we're going to see for SO3, and it ultimately stems from the fact that the boundary identification process here is completely different from the case of the ball. Okay, so now let's come back and look at the case of the ball. Okay, so here we go. So now we're going to draw a picture. All right. So imagine, so this is a solid ball. Here's the origin. Remember, the origin of the ball corresponds to the identity, meaning you're just staying fixed in space. And now, let's imagine that we go up through the ball, like maybe, in fact, let's literally go up, for example. Okay? And, right, that's like we take the, right, the unit vector k, and we start, this is a collection of rotations around the vertical axis by angles that start small and keep growing. So you're slowly rotating. So as you move, this is our space of rotations. This picture with the boundary identification is our space of rotations. And as you move up this line, these points correspond to rotations that are going around and around. and then when you get to the end, you've done it by 180 degrees. Okay? Now you come out from the bottom, and you return. So this path that starts here, goes to the top, comes from the bottom because of the boundary identification. This is a closed loop in the space SO3. Okay? If you just think about the ball without the boundary identification, it's just a single path, and you can easily contract it to a point by bringing the ends together. But here, like with the torus, you're kind of stuck. You can try to move, but if you move this, then this has to move also. Right? So you're... Right? So it's not obvious, of course it can be proved mathematically, this is a loop, this is a closed loop. In SO3, right? You've spun all the way around and come back, but it's not evident how you can shrink this to a point in the space of rotations. Now watch, in fact let me write this down here. So this picture here is a closed loop. Now what I'm going to do is do it twice. So I go up, come up from the bottom, and now I'm going to go up a second time, and then I'm going to come back a second time. I'm drawing them slightly apart just so you can see the two separate things, but imagine they really go on top of each other. This path from here up, down, this corresponds to spinning around twice. Now watch this. So now I'm going to draw the picture again, and now imagine we go up, and then we come back, but now I'm going to, I'm going to just kind of move the second path a little so that it veers a little bit away, and then I come back from the bottom and I come back to where I was. So this is, again, this is a slightly deformed version of the double loop. Okay, here it is again. So now I go up, and now again you can keep tilting this around. Now go up, and then you come back, but when you come back the second time, imagine you veered off to the right, and then you come back. So this is a deformed version, continuously deformed version of the original double loop. Now if you keep doing this, so let's go up, we come back, but now we tilt down, and then we come back. Okay, and so what I'm doing is I'm looking at different loops in the space that are continuous deformations of the original doubled loop. Okay, so now let's do it again. We go up, we come back, now we go down, and then we come back. So this path is actually a deformed version of the original doubled loop, but now something magical happens. So let's go up. We come back, and now the second time, when we come back, let's stop a little bit before we get to back where we were. Let's stop here, and then turn around, and then come back. Oh! Right? You see, you go up and back, and now here you go all the way back, turn around and come back. But now you go up and back, and let's stop, epsilon of a meter before, then turn around. Now you can maybe hopefully see what's going to start happening, which is you can go up, come back, and okay, keep turning around sooner and sooner. You see, now you see that as you make the turnaround point come sooner and sooner, it is going to start collapsing and come all the way back. And if you do this enough times, eventually you'll even get to the picture where you don't ever even cross the boundary at all. You just come to here. Oh, maybe I started turning around. Yeah, you don't even turn around, so the color doesn't even change. You just come back. And anyway, okay. So I hope that makes sense, right? So you see, this is a very completely different geometry. All right. The boundary identification is very different. So this shows the funny thing. Now, of course, the whole point is now I want to explain to you what the heck this has to do with the belt trick or the Moog trick. So this is a funny phenomenon that in the space of rotations, you have a certain closed loop that doesn't seem like it can be kind of contracted to a point. But if you do it twice, unlike the case of a donut, when you wrap around a donut twice, it gets even harder to disentangle. Here, if you do it twice, it magically can be contracted to a point. Okay? Yes?
This didn't have to do with 3D, did it? It's if I just flip the direction of the
Are you talking about the asteroids or this?
the fact that you get a
No. So this doesn't have to take place in 3D, but in this picture, I'm referring to the space of rotation. So
Okay.
this is where it's. But you're right that the whole argument really takes place in a planar slice.
And if I flip the direction of the red and yellow identifications on the top right side.
Right. So what's going on in the case of the asteroids game is if you flip some of these identifications, you wind up getting what's called the real projective plane. Anyway, I don't want to get into that here, but yes. So if you start changing the boundary identifications, the topology will completely change. Okay. So anyway, so this is the kind of key point here. Now I want to explain what does any of this have to do with this business with my arm. Okay. So this is the the next topic. So now we want to come back to the mug trick. Are there any other questions? Yes?
When you talked about...
Well, I'm going to first drink some of this liquid since I don't need this anymore. Yes?
So when you talked about how 2 times rotations kind of collapse to a point,
Yes.
is that kind of equivalent of not rotating at all? Like, is that what you're mentioning?
Well, okay, so this is, I mean, you're literally, what you're saying is that the process of spinning around twice can be continuously transformed into doing nothing at all within the space of rotations. So this is a visualization of it. Now I'm going to want to explain what does this mathematical thing. I claim that what I was doing with my, now it does, the top is on, I can turn it up again. So what I was doing here, I claim is illustrating this phenomenon. Of course, there's no reason, if mathematically you could deform something, there's no reason that it has to be realizable using the arm of the human body. Right, because that's constrained to certain physiological conditions that aren't required in the math. But this is what we're going to see is being demonstrated by this motion with my arm. Okay? Then we're going to see that we're going to introduce quaternions, and that will give us a different way to visualize what's going on here. Okay?
Thank you.
You're welcome. Okay, so let me first drink some of this liquid. Okay, so let's draw a human arm. Again, with 3 fingers. And we're going to imagine measuring the positions along the arm using a parameter x, which goes from 0 to 1. And at each point, just imagine this is the initial position of my arm. And at each point, we're going to have a little orientation frame. So here's I. And then here's, well, let me actually put the I vectors everywhere. So pointing out of my arm. Okay? And then we have J. And then we have K coming up. Okay? So the point is, you imagine that at every, okay, I realize this arm is now the opposite, anyway. So at every point of my arm, visualize a little reference frame based at each point. Okay? Now as my arm moves around, ignore this point of my arm happens to move, but ignore the spatial translation. Just pay attention to the fact how the oriented frame is moving. Okay? So what I'm going to do is I'm going to let sigma x of t in SO3. So I'm going to imagine doing this, doing the entire mug trick over a time interval of length 1. I'm going to let sigma x of t be the orientation based at point x at time t. Okay? X equals 0 corresponds to my shoulder. X equals 1 corresponds to the end of my arm. Okay? Now, what happens at my shoulder? So let me get this mug again. Okay? So if you imagine an oriented frame at my shoulder, in principle, nothing is happening at my shoulder. Okay? I mean, again, there might have been some wobbling, but imagine I was slightly better at it being a contortionist. So the point is, this is the identity for all time. Okay? So at the shoulder, the frame is never moving. It's staying fixed. What happens at the other end? This is the double loop. Okay? So over a time interval of length 1, this was the R4 pi t 00001. Okay? So this is, now what's happening in between? This is very important. Halfway through the trick, what's happened at x equals 1 is back where it was. X equals 0 never happened. But everywhere in between is completely screwed up. Right? That's this double twisting. So the point is that sigma x of a half is not the identity for x between 0 and 1. So in other words, if you look at what happens at a fixed x over the time interval from 0 to a half, this is not a closed loop in SO3. Precisely because, right, halfway through the time, right, every point that wasn't at the end is twisted out of shape, right, because my arm is completely, right, double twisted, okay? But if you look over the entire time interval, this is a closed loop. This is the entire point of all this. What does it mean? The fact that I did this, come back, oh, now I'm back where I began. So at every point of my arm is back to the identity orientation. Back to the identity. So at the far end, sigma x of 1 is the identity for all x. Okay? Not at 1/2, but at time 1, everything is back where it began. So now let's look at each point of my arm. So let's consider the collection as x goes from 1 to 0. This is a kind of continuous family, continuous collection of closed loops in SO3, where at x equals 1, it's the double loop, and at x equals 0, it's the constant loop that does nothing, sits there for all time. So if you follow at each point of your arm, right, if you follow what's happening to those orientations, then at one end of your arm, it's the double loop in SO3. At your shoulder, it's the identity point constant path. And all the points along your arm are a continuous family. Each individual point is a closed loop because sigma x of 1 is always the identity. For fixed x, sigma x of t, for t going from 0 to 1, traces out a complete closed loop in SO3. And so as x moves from 1 to 0, then you've continuously deformed the double loop to a point. Okay? So does anybody have any question about that? We're now going to turn to quaternions. Yes?
So when you did the demonstration, you did like upper, below, lower arm.
Yes, so the fact that I had to put the upper and lower, this has to do with just trying to realize, using the physiology of the human arm, this business, right? And by the way, I should say, I'm not claiming that the exact, what we call homotopy, this exact collection of deformations realized with my arm is exactly the same as what's going on in the other picture. Probably it's the same, I just haven't thought about it, okay? But in any event, there's no reason, like mathematically it could have been the case that there's this fact that this thing is contractible, but the fact that you can realize it using a belt, and by the way, with the belt, the idea is similar. You just imagine a little reference frame at each point x along the belt, from one end to the other, and then you follow at a fixed point, follow what it's doing, and this is also witnessing the same phenomenon. But the fact that it can be realized using a physical object twisting in space, this is not a mathematical fact. Somebody had to discover that this is possible. Okay? So it's like a bonus that you can actually witness it using this kind of thing. Okay? Does anybody have a question about that? Okay, so now we're going to turn to quaternions. This is section 4. I think there was probably something called section 3 that I Forgot to label double loop discussion with section 3. Okay, this is going to give us another visualization of the contractible double loop. Right, so contractible is what we say that you have a loop in a space, and you want to say that you can continuously shrink it to a point within the space, here the space being the space of rotations, without snipping it. Okay? So I want to visualize this contractibility of the double loop in a different way. Okay, and this is going to replace the geometry, or topology if you like, of SO3 with that of S3, the unit sphere in R4. Right? Why do we call the unit sphere in R4 S3?
It's a three-dimensional sphere.
Right? Because it's kind of three-dimensional, right? You cut out one condition in four-dimensional space. Okay. So we're going to make a relationship between the unit sphere in 4 space and the space of rotations. Okay? And this is going to be where quaternions come in. And I should say that among this is going to be a kind of give rise to a refinement of rotations. This is related to certain things called spinors. And these things that kind of refine rotations are extremely useful in a variety of applications of spatial rotation. So among the applications of what I'm about to discuss is, first of all, smooth motion in video games. So what do I mean by smooth motion in video games? Video games are flight simulators, basically computer graphics. Okay? And the issue is that if you try to describe, let's say you're like doing a helicopter game or something, and if you try to describe rotations in space using the viewpoint of SO3, this is going to relate to something called Euler angles, then when you pass through certain funny positions, then there's a lot of jumpy behavior. But another issue that this is, which as we'll see, another issue that this is related to is there's this phenomenon of something called gimbal lock. And what this refers to is the following, that, so when classically, of course, in the 1600s, when people were going by ships, they navigated using stars. But in the 1960s, when people started going to outer space, then they had to have a way of figuring out their orientation in space without having an external reference frame. And so they use these things called gyroscopes, which involve three different axes, okay, each with a kind of circle on it. And the positions of these 3 circles relative to each other would encode something called Euler angles, okay, which is a way of encoding spatial rotations we'll discuss at the end. And the problem was that, so as your spaceship was moving in space, these things would kind of move around. But if 2 of them wound up becoming parallel, if 2 of these moving circles wind up coming into the same plane, then they have no way to decouple. Right, and then you kind of lose a degree of freedom, and then your spaceship can't find out where it is. Okay, and this was have any of you seen the movie Apollo 13? Yes, if you haven't, you should definitely watch it. It's an awesome movie. Anyway, so in that film, this is something that, of course, really happened, that they were trying to go to the moon, and then they had this explosion on board, and they had to figure out how to get back, and they lost a lot of the computer guidance system, so they had to use a gyroscope. And then they had to be very careful not to orient the ship to get close to this gimbal lock position, because then they would have no way to kind of figure out where they were. Okay, so now let me tell you what quaternions are. So Hamilton was trying, after people realized that complex numbers were just a kind of multiplicative structure in the plane, then Hamilton tried for many years to discover a way to do multiplication in 3 space. Now, we all learn about the vector cross product, but what they don't usually discuss in the physics classes, the vector cross product mathematically kind of sucks. It's not associative, for example. It happens to have other nice features, but the vector has no identity, right? So the vector cross product has some deficiencies. Hamilton eventually discovered these things called quaternions. They're called H in his honor. So this is the collection. Can be realized in several different ways, but this is the collection of 2 by 2 complex matrices having this form. alpha beta minus beta bar alpha bar. Okay? Now we can write this, if I'm going to write alpha as a plus bi and beta as c plus di, then I magically jump to this point. Okay, great. So 1ijk, right. So this is So this is a collection of matrices that's four-dimensional over the reals, and then one just calculates directly that if you multiply I and j, that you get k, and that happens to be the negative of j times I. And more generally, one writes a little cyclic picture, I, j, and k going around. ij equals k, jk equals I equals minus the other way around, and then ki equals j equals minus the other way around. And also I squared, j squared, and k squared are all negative 1. Okay? So the point is, if you multiply any two such expressions, you get another expression of this type. So this number system is called the Quaternions. And now we're going to see this is extremely different from 4x4 real matrices. So if I give you a quaternion, A plus BI plus CJ plus DK, whoops, then I define its conjugate by negating this so-called imaginary part. That's called Q conjugate. And then one can check that if you multiply a quaternion against its conjugate, you actually get a scalar matrix. You get the real number determinant of Q. But if you look at these things, the determinant of this is alpha squared, alpha bar squared, absolute alpha squared plus absolute beta squared. This is a squared plus b squared plus c squared plus d squared. Alpha squared plus beta squared. That's always positive when Q is not 0. So this is extremely interesting, because what it says is that every non-zero quaternion has a multiplicative inverse given by the conjugate divided by the determinant. Okay? So this is a very interesting thing. Unlike 2x2 real matrices, in the context of quaternions, every non-zero quaternion has a quaternion multiplicative inverse. Okay? This is very unusual. All right? This is actually really phenomenal. And now what we're going to do is we're going to consider what I'll call I, which is the collection of pure imaginary quaternions, the ones with no real part. How do you characterize these? These are the quaternions that when you conjugate, you get the exact negative, because this part isn't there. So this is going to be the collection of quaternions whose conjugate is the negative. All right? This is the pure imaginary stuff. Ri plus Rj plus Rk. Now here's the beautiful thing. We're going to consider how a general quaternion conjugates this pure imaginary 3 space sitting inside. So let's consider, for a given non-zero quaternion, this is a 4-dimensional space with a point removed, so it's connected. We're going to consider the operation of conjugation, where we think about I as being a copy of R3, and to each vector, we conjugate it by Q. And now I claim that this is again in the 3-dimensional space I. Well, how do we characterize this 3-dimensional space of pure imaginary quaternions? They're the things whose conjugate are equal to their negatives. And another property of conjugation I should have mentioned, which is not so hard to check from this recipe, is that if you conjugate two numbers, it's the product of the conjugates in the other order. Basically because inversion of a product is the product of the inverses in the other order. So, if we conjugate QV Q inverse, we get Q bar inverse V bar Q bar. V bar is minus V, because I'm assuming V came from this pure imaginary space. And Q bar, right, is Q inverse times the determinant. So this is Q inverse times the determinant, and this is the reciprocal. So it's Q times the determinant inverse. Those cancel out, and then you get the minus. Voila! So the non-zero quaternions, under conjugation, act on this three-dimensional space. So you get all non-zero quaternions, this multiplicative group of non-zero quaternions, acts on the space, this three-dimensional space. What kind of linear transformations do we get this way? Well, the length of a quaternion was the determinant of the matrix, but if the thing is a pure imaginary, that's just a 3-vector, its length, the sum of squares, the usual length squared, but the determinant of QV, Q inverse, is the same as the determinant of V, as a quaternion. So this says that these are rigid motions, length preserving. This says that the conjugation preserves length, but it does better than that. It also preserves orientation, because if you associate to each quaternion its determinant of the conjugator, well, as a rigid motion, its determinant must be plus or minus 1, but these come from a connected space, the non-zero quaternions. So therefore, you can't jump the determinant. So the determinant must always be plus 1. So we always get, in this way, from any non-zero quaternion, we get an element of SO3. When you do this, in this operation, if you scale the quaternion by a real number, it cancels out. So to get this effect, you could scale the quaternion to be a unit quaternion, to have length 1. Okay? Now what do you get in this way? Now comes a beautiful fact, which has the proof of what I'm about to say in Wikipedia is horrible. There's a much more elegant proof that I don't have time to discuss here. The following fact, that if your quaternion, if you write it as cosine theta plus sine theta times u, where this is some pure imaginary guy, so u is a pure imaginary, then the conjugation turns out to be rotation by 2 theta around u. Oh, that's interesting. So since we know by Euler's axis angle interpretation, every rigid motion of space is rotation by some axis by some angle, then you get everything in SO3 from a quaternion. And if you limit yourself to the unit quaternions, then you're getting everything, and the only ambiguity, this is a homomorphism. If you compose conjugations, it's like composing multiplying the things you're conjugating by, and the only things that become trivial, this turns out to be a 2-to-1 map, that the kernel is exactly plus or minus 1. It's just a direct calculation. But this is the sphere in R4. So, the sphere in R4 is a 2-to-1 cover of the space SO3 via this quaternionic conjugation operation. Now this will give us a beautiful new visualization of the double loop contraction as follows. So here, of course, I can't draw a picture of S3 because I can't draw pictures in R4, so we're just going to be impressionistic. Imagine that that's the sphere, the unit sphere in R4. This is our S3. There is a point on it which corresponds to the unit quaternion. There is another unit vector corresponding to K. And then you have a circle in here corresponding to the double loop. You have a collection R4 pi t. Well, sorry. We have this motion here. Sorry, cosine, let's say 2 pi t plus sine 2 pi t k. Sorry, I should have put a 1 there. Sorry. So this is a circle in the plane spanned by 1 and k. So in this thing that sits inside R4, we have a circle. Now, what happens when you send this to SO3? This quaternion by that discussion that we just had over there, this goes to rotation by 4 pi t around k. So, in this quaternionic unit sphere, there's a circle whose corresponding rigid motions of space, as you move around the circle, this gives you the double loop. But I claim in this sphere, what happens if you take this plane that's cutting the sphere, it's a two-dimensional plane in four-dimensional space, now you start tilting, this is cutting it, now you start tilting the plane so it still passes through one, you will get a smaller circle as it cuts. And as you keep kind of pull the plane, slide it so it keeps passing through one, but cuts less and less of the sphere. Right? Imagine it's like in usual space, right, if you had a plane cutting the North Pole in a great circle, and as you tilt the sphere, the way it cuts will be these smaller and smaller loops, and then until the plane is tangent, and then it'll be a point. So in this space, we have this collection, and they shrinks to a point. Great. So now you just send these into here. That's a collection of loops in SO3 that go from the doubled thing to the constant thing. Now, what would happen if you only considered rotation by 2 pi t? This is for t going from 0 to 1. If you considered the rotation by 2 pi t around k, then back here, you would actually not have a closed loop. That's the problem. Okay? So from the quaternionic point of view, we also see this contractibility, and the doubling is exactly related to this connection here. Okay? Now, the beauty of this stuff, we didn't have time to discuss Euler angles, I apologize, is classically people describe rotations in space, and maybe they still do in physics classes, using Euler angles. You basically consider, imagine, if you will, you're trying to describe, you have a plane, you're sitting in a plane that might be upside down. If you want to describe how the plane is oriented in space, starting from being on the ground pointing in some direction, first you would figure out your heading, right? Then you would figure out your pitch, and then you might tilt the plane. Okay? So this heading is, that's a rotation on one axis, so this is called yaw, and then there's pitch and roll. And so every rotation can be described in terms of three basic kinds of rotation. So if you look at the Apollo 13 movie, you'll see Tom Hanks scribbling to figure out these Euler angles and asking these guys at Mission Control to compute the roll, pitch, and yaw to double check his arithmetic. But anyway, the point is that Euler angles have the deficiency that when one of the yaw, pitch, or roll matrices, when the angle hits 90 degrees, then the resulting rotation only depends on the difference of the other two angles. So you lose a degree of freedom. And physically, that's realized by the gyroscope having two of the circular parts coming together. But the beauty of quaternions, you see, is here, when you come back to where you were by one rotation, in the quaternions, you have not come back. You're very far away. So if you describe rotations using quaternions, the gimbal lock phenomenon doesn't occur. But there's one problem. In 2008, a guy named Michael Schuster introduced quaternionic multiplication into the software at JPL, but he decided to define the multiplication of quaternions using the opposite order. And this causes problems when the space shuttle tries to dock with the International Space Station. And so in the aerospace community, there's now a tremendous problem, which is that there's part of the community that defines quaternionic multiplication the opposite way around, and which is completely inconsistent with the rest of physics and mathematics. And so every time they're doing any of these applications, because quaternions are great for certain aerospace purposes, they always have to make sure that this so-called flip multiplication is not being used. And let me just, I didn't bring it with me, but anyway, there's a paper by some people trying to urge the community, please stop using flip multiplication. But, it's stuck. So in any event, so quaternions are very nice because they avoid this problem of the jumping phenomenon when you lose this degree of freedom, because in the quaternionic space, the corresponding points are far away. So some of those difficulties disappear. Okay? All right, I'll stop there.